Welcome to today's Fundamentals and Application of Outdoor Reset online seminar. Today's presentation will be about an hour in length and is worth 1 PDH credit. I just wanted to take this moment to introduce myself. My name is Marina Getling. I'm the Viessmann Academy Manager here in the US. And I also wanted to welcome you and say thank you for attending today. I hope you're all having a great Tuesday so far. I also wanted to take this opportunity to introduce you to your instructor today for those that may not know him. Will be Jody Samuel. Jody is a graduate of Maine Maritime Academy with a degree in marine engineering. Over the past 20 plus years, he has worked with various companies, including Amtrol, Viessmann, and Caleffi, serving in various roles, including application engineer, product manager, training manager, and manager for engineering education. Currently, he serves as the project development manager for Viessmann US. And before Jody begins, I do have a few housekeeping items to go over. And the first is, as I stated, it is worth 1 PDH credit. And if you selected yes on the registration process, we will send out the certificate within 5 to 7 business days. However, there is a required survey through RCP that we will email out to you by the end of the day, which must be filled out to get that certificate. If you aren't sure if you selected yes in the registration process, feel free to email us. We'll have the email on the last slide of today's presentation, and we will double check for you. Everyone will stay muted throughout the entire seminar. However, at the bottom of your screen, you will see a Q&A button. If you're on a desktop laptop version, this is what it'll look like on the left, and a mobile device version is on the right. And you can type in any questions you have throughout the entire seminar. Jody will stop about halfway through and at the end to answer any questions submitted. And then we'll also put together a Q&A document that we will send out to you in the next week or so with all of the associated answers. So feel free to type anything in there that you may have a question on. We are recording today's seminar and it will be posted on the video library on the Viessmann-usacademy.com website. And once you're on that website, you can simply click in the video library in the header of the page, or if you scroll down, you will see the larger video library section. And once you click into there, this is what you'll see. Up top, we do have that search function. You can simply type in outdoor reset, fundamental and application of outdoor reset, and the video will populate. Or we have that recorded online seminar section in the drop-down menu. You can click on here and see this recording and all of the other online seminars that we have had this year. Since this is a collaboration with the Viessmann Canada, this will also be on our YouTube channel. And once you're on youtube.com, you type in Viessmann North America and our page will populate, and you'll be able to find this recording and a bunch of other videos we have amongst the Viessmann North America group on this channel. And with that being said, let's begin. Here is Jody.
So today we're going to talk about outdoor reset control. So before we get into it, let's go through a couple of housekeeping. Really don't need to talk about this. Miranda already covered this in her part of the introduction. The presentation is copyrighted. If you'd like a copy of it, when you fill out the survey, just make a note in it, and the Academy can get over to you a PDF version of it. And let's move on to the purpose and learning objectives. In reality, I jumped down to the learning objectives on the bottom. So when we finish this presentation, you should be able to explain the heat flow process from the burner to outdoors and how outdoor reset can control it. You'll be able to list the benefits of outdoor reset control, explain how outdoor reset works, and finally describe the process selecting a heating curve for the application. For me, this is always a timely subject from the aspect of, there's always a lot of discussions on projects, either looking at the documentation or talking to somebody about, the application and really, how should they approach outdoor reset. Now, when we look at outdoor reset, it really is really looking at part of the process of heating a building. And I always laugh when I start to think about this, having had now have two 20 some odd year old sons. And, one of the things that I'd always tell them when they left the door open is, close the door, we're not paying to heat the outdoors. When in reality, when you look at the heat loss of a building, we are actually paying for heating the outdoors because of the heat loss of the building, but the goal is to minimize that in the process. When we look at this heating and looking at controlling it, what we're really focusing on is really there's essentially three heat transfer processes that we're concerned with. So if I start from the outside, There's going to be a heat transfer process from the living space to the outdoors. There's our heat loss. We're going to have some sort of heating element in the building. There's a heat transfer that happens there from our hydronic water to the living space. And then internal to our boiler, we're going to have a heat transfer process from our combustion gases into the hydronic water. And when we start to look at this process, we want to be as efficient and effective in this process. And ultimately, we also want to make sure ultimately that over here, our building living space is going to be comfortable. So really, those are really what we're trying to achieve here. And we really need to have a look at how outdoor reset fits into this, really from an aspect of comfort and also from an efficiency standpoint. Now, when we look at this process, there are a couple of points here that normally are, I'm going to call them fairly close to anchored. Okay. So if I'm burning natural gas, my combustion temperature is going to be somewhere in the neighborhood of about 3,000 degrees. You will see numbers higher, you will see numbers lower as well. Depends on the makeup of the natural gas, because it's not a pure gas. And then it also depends on how much excess air is applied to the process as well. When we start to look at this heat flow from the combustion chamber to the outside, this point here is fairly well tied into a fairly tight band on temperature. Same thing as with combustion. In most cases, the building living space is usually a tied-in point as well. Here I have 70 degrees Fahrenheit. If you're running off the metric system, you may be looking at maybe 20 or 21 degrees Celsius, which is pretty close. And so there's not going to be a lot of variation that happens here as well. But when we look at the entire process, okay, from the aspect of what we do, there really is one point that we can control. The hydronic water temperature. We can design and we can control what that temperature is doing, but it becomes a question of what are we going to do with that water temperature. Equally as important as the other big variable is the outdoor temperature. Because the outdoor temperature changes dramatically, both in aspect of changing geographically. It changes from at that point of where we're located. Am I in Bangor, Maine, where I might be looking at a minus 15 degrees Fahrenheit? Or am I as my design outdoor temperature, or am I out in LA, Los Angeles, where the outdoor temperature for design dates may be 45 to 48 degrees Fahrenheit? And additionally, that outdoor temperature changes. So when we start to look at this process and trying to control the flow, we have a couple of points that are fixed. We have a variable point that drives the process. And we also have a variable point where we can adjust and control the process. And that's really when we start to look at what we're trying to do. We're trying to control this heat transfer process to be as efficient, but also to maintain comfort in that living space. Now, for our discussion, we have to start somewhere. So let's quickly kind of drop and talk a little bit about heat loss, and then work our way back and talk about really hydronic water temperature. So, every project has a starting point. When we start to look at heating a building, the thing that we have to figure out is how much heat does that building lose? Because from an aspect of heat transfer, the heat will move from hot to cold. Okay. The bigger the temperature difference, the more heat that's going to come out of the building. So we start to look at colder climates. If I did a building of the exact same construction, that building will lose a varying amount of energy depending on the outside temperature, whether it's the design temperature changes or whether it's just because of the varying nature of the outside temperature. So we start to look at heating a building. There is a design condition that we design for, but that number changes day in and day out. Just as the outside temperature changes the amount of heat the building loses, also the construction of the building. Is it well insulated? Is it fairly tight from that aspect? Or does it have less insulation and it's a drafty building? So all of this really comes into play when we start to look at how much heat we have to put in the building, because ultimately our objective is a fairly consistent temperature for comfort of the occupants. So what we're really looking at here from an aspect of that heat loss is it's all about heat transfer through the envelope. So let's say that we're designing for a 70-degree temperature on the inside, and let's say we're designing somewhere around 0 degrees Fahrenheit. For me, that's somewhere around Boston, Massachusetts, up to probably southern New Hampshire. So we select our inside temperature. From ASHRAE data, we pick our outside temperature, and then that delta T, or that differential temperature, then sets the rate of heat loss. Now, from an aspect of design, we don't just look at the delta T, we also look at the wind speed blowing on the boiler, because on the building, because that affects heat loss as well. But from all of this construction, from this information, and through utilization of some sort of program or resource to generate a heat loss, this happens to be an old school IBR longhand heat calculation, we can calculate how much heat the building is losing. Old school is longhand calculation. Nowadays, most of it's done through a computer program. This happens to be RightSoft, a program that I've utilized in the past. But the heat calculation is done. Once the calculation is done, we have now figured one of the pieces of puzzle, the main component of designing that heating system. We know how much heat the building is losing under design conditions. So we know how much heat has to be put into the building space, and we know how much heat has to be put into the hydronic water. So now we've kind of hit a balance point all the way across. Now, the one thing that we haven't touched on yet, though, is really the hydronic water temperature. So I've got to set that hydronic water temperature. That water temperature is tied to how comfortable the building is going to be, but also from an aspect of performance, when I start to look at and select the water temperature, that water temperature affects the heat transfer and the heat exchanger of the boiler. So the water temperature also plays into how efficient we can be in taking that heat that's being generated in the combustion process and extracting it into the water to heat the building. Now, as far as the choice for water temperature, there's a lot of temperatures that are out there that people normally probably will throw at in my direction when we talk about designing systems. You know, a lot of times they'll say, well, is it going to be low, medium, or high temperatures? You know, low temperatures, generally, most people say somewhere under 120 degrees. Medium, probably 140 to 150 on the high side. The higher temperature ones, you know, those are the stuff that in the 180 to 190 degree range. So if I'm doing high temperature, a lot of people look at doing thin tube baseboard or an air handler unit at your high temperature. So from a design standpoint, when I look at this design water temperature based on the methodology that I am using to heat that building, a lot of times that locks me into a bracket of potential temperatures for the water for my heat emitters. So if I choose my heat emitters, and I'm going to go looking at, for this, really the high temperature ones. This happens to be performance numbers for a baseboard. It's a slant fin baseboard. Down here are performance numbers for an air handler. It happens to be a first company air handler. But when I look at selecting water temperatures, typically when I'm looking at baseboard or air handlers, a lot of times the selection of the water temperature is based on the preference of the engineer or designer of where they want that water temperature to be. Because if I do baseboard, for instance, and I'm flowing at 4 gallons per minute, typically the design point most people will say is I'm designing for 180 degrees, and 180 degrees will give me 610 BTUs per linear foot for this baseboard. I could also design down at 150 degrees, and I'm getting about 400 BTUs per linear foot, about 2/3 the energy. So you can always select a different water temperature for design. It's just as the water temperature goes down, the amount of heat per linear foot for baseboard goes down. So if I have a target heat loss of the building, it means I need more heat emitter. Same thing happens when I look at air handlers. When I do an air handler, I can select a flow rate, a blower speed, and then a water temperature. So let's say I decide that I want the supply water temperature to be 180 degrees, and I flow at 2 gallons a minute, there's 50,000 BTUs per hour. But from a design standpoint, when I start to look at putting the right size heat emitter to heat the building, or I'm putting enough heat emitter to heat the building, a lot of times the discussion is, this is a heat emitter I want to use, this is the water temperature, now let's see what combination works. You know, a little side note over here, if I'm doing radiant, typically from a radiant standpoint, the water temperature is going to be determined by the application and a software package to design it. So in radiant, we say this is how we're going to design it. The program tells you what the water temperature needs to be. But from an aspect of outdoor reset and heating the building, through one of these methodologies, we will then pick a water temperature so that my system can be balanced. So I come back here, my 70-degree room temperature, my 3,000 degree combustion gases. My outdoor temperature on the design day is going to be 0 degrees Fahrenheit. And based on my desire, I'm going to say I'm going to do 180-degree water temperature out to my baseboard. Then I'm going to make sure that I'm flowing at the right rate and I have enough baseboard in that house so that with 180-degree water at design flow rate, I am putting the right amount of energy into the living space that on a 0-degree day, it matches the energy that the building is losing to the outside. So that becomes our goal really in this design process. But here, I've now chosen 2 of my design conditions when I'm looking for the setup of my system. On the design day, which I've identified at 0-degree outside temperature, I need 180-degree water based on the heat loss of my building, based on my flow rate, and based on what I've chosen for a heat emitter and how much of that heat emitter goes into the building. Now, additionally, based on this selection of 180-degree, little side note here, I've now also looked at how efficient, I've really set the yardstick of how efficient the heat transfer can be from my combustion gases into my hydronic water inside the heat emitter inside the heat exchanger of the boiler. So not only am I affecting comfort in my decision here, but I'm also affecting efficiency. Okay. And from an aspect of design, if everything is designed right, on a 0-degree day, 180-degree water, I'm putting the right amount of energy into that building that the boiler and the pump, the flow rate, everything is running at 100%. The exact amount of heat going in as the exact amount of heat going out, and everything stays balanced. And again, this is under ideal type conditions with no internal or external gains that aren't accounted for. Okay. Now, the thing we start to look at these kind of conditions is I am designing for a very specific time period. So if I was designing for 0 degrees Fahrenheit, and my chart here has been skewed a little bit from my changeover from PowerPoint to Google Slides. But if I look at this 0-degree day right here, 0-degree actually should be over here. I am designing for a condition that, if I look at a spread from about 7 degrees Fahrenheit to 0 and 0 to -13, I'm designing for a little bit more than 2% of the heating season. So we design for 2% of the heating season because the goal is to be comfortable under design conditions. But when you start to look at some of these things here and these numbers here, you notice when I look at buckets up or bins up here, above 28 degrees Fahrenheit, above 41 degrees Fahrenheit, above 54 degrees Fahrenheit. This represents a large portion of the heating season. And under these conditions, I do not need the same amount of energy that I do on my design day here of 0 degrees Fahrenheit. Okay. So when we start to look at designing, and then we carry on to actual operation, this is the conditions for my example that I'm designing for. 70 degrees on the inside, 0 degrees Fahrenheit on the outside. And that gives me a certain amount of heat transfer. But this building is sitting here, I'm going to go back to Boston, Massachusetts. This building sitting in Boston, and not every day is 0. Okay. On that 0-degree day, I have a 70-degree delta T driving heat transfer through that wall, which ends up being a set amount of heat loss in BTUs per hour that building is losing. Some days, the temperature is only 35 degrees. Okay. So on a 35-degree day, I'm now 35 on the inside and 70 degrees on the outside. that represents only about a 35-degree delta T driving heat through the building's structure. So now it's a 35-degree delta T versus a 70-degree delta T that I've designed for. So if I have half the delta T, I only have half of the heat loss. So all of a sudden, this building that was designed for design conditions, if I don't do anything to balance the rest of the process, I'm putting twice as much energy into the building space than is needed to heat that building. So from an aspect of comfort and control, I have to figure out, how do I vary the amount of energy that's coming into the building when the outside conditions change? And ideally, to do that, I'm really trying to maintain comfort in that building. Okay, so the question then becomes, what's my options? How can I maintain that comfort? The old methodology, the old school version, and I say old school, it still is fairly prevalent nowadays, is, well, the first thing I probably could do is pulse the building with heat. So what I talk about when I'm pulsing the building is I don't change anything. My living space stays the same. My boiler water temperature stays the same. So when the outside temperature changes and this number changes, how I'm going to affect the process is I am going to, instead of running continuously on the flow through the heat emitter, I'm going to periodically turn the pump on or open a control valve, apply water to my heat emitter, pulse the building with heat, if you will, until the thermostat controlling the temperature is satisfied. At that point, I stop that pulse of heat. So I turn the pump off or shut a control valve. My heat emitter stops releasing heat until the thermostat drifts down through its differential and says, okay, it's time again. So if I need half the heat, basically the thermostat controls either a control valve or a zone pump, if you will, to apply flow to my heat emitter for about half the time period. So it might be 3 minutes on and 3 minutes off, 4 minutes on, 4 minutes off. But the end result is, after that 1 hour period, if I look at my control valve open time versus closed, or my pump on time versus off, it's 50% on either side. Okay, so this stays constant, this stays constant. This will vary a little bit because of the thermostat, but the end result is I'll get a pretty decent balance between the two of these. Okay, the thing is, there is variation here in temperature, and I didn't do anything here. Nothing here improves because I'm still staying at the same temperatures. Okay. But from an aspect of simplicity, it's a very simple way to approach it, and it's one that's been used effectively for quite a few number of years. A lot of times when somebody says, can we balance it better? The question always comes up is, when I pulse the building, I'm looking at a fixed flow rate. Question comes up, well, what about varying the flow rate? Can I change the output of the heat emitter by changing the flow rate through that heat emitter? Okay. Now, when that question comes up, a couple of things that have to be pointed out, and the real answer is, from the ability to accurately control it, it becomes very difficult. Okay. Let's go back to our heat emitters and take a look at the performance numbers. And I'm going to concentrate still back to the 180 degrees, but I want to look at two different flow rates here. One is at 4 gallons a minute and one is at 1 gallon per minute. So with baseboard, if I'm flowing at 4 gallons a minute, I'm getting about 600 BTUs per linear foot. If I drop that temperature, that flow rate down from 4 gallons per minute to 1 gallon per minute, I'm now down to 1/4 of the flow rate I originally had, or 25% of the flow. But if you look at the numbers here, I went from 610 BTUs per linear foot just down to 580. Okay, so I've reduced it down to 1/4 of the original flow, but I'm still getting about 95% of the energy out of that heat emitter. So all of a sudden, if I'm looking at trying to balance the system out and I'm trying to vary the flow rate, you'll find that I don't end up with a nice response, that I have so much change here in the flow rate, and I get a corresponding change in the amount of heat that's coming out of the heat emitter. Makes it very difficult to control and deliver based purely on changing that flow rate. The other thing to consider, especially with baseboard, is as the water goes through the baseboard, the temperature drops each foot as the heat is being emitted. So at 4 gallons per minute, at this BTU output, I'm seeing about a drop of about 0.3 degrees per foot. If I slow it down to 1 GPM to get 580 BTUs per linear foot, the amount of drop I'm seeing increases from 0.3 degrees Fahrenheit per foot to 1.16 degree Fahrenheit per foot. All of a sudden, if I have a series loop and I have a long run with a lot of baseboard, all of a sudden the performance concern comes out where I'm worried about how much BTU per linear foot's coming out of the baseboard at the end of the run versus the front end of the run. So when somebody says, well, what about varying the flow rate? With baseboard, it becomes very difficult to adequately control the heat transfer based purely on just changing the flow rate, and also getting consistent performance through all combinations of flow rates at both ends of the baseboard runs. Same thing happens with air handling units. So if I look here and I say at 6 gallons per minute, and I look at it from 180, at 6 gallons a minute, I get 100,000 BTUs per from that heat emitter. If I drop it down to 2 gallons per minute, I've dropped the flow rate down to a third of the original flow rate. But if you look at the numbers here, I'm still getting about 79% of the output. So again, just when somebody says, well, what about, varying the speed through the heat emitters? The problem is you generally don't get a good proportional change. As I drop the flow rate, I can drop the flow rate quite dramatically, but still the output still stays fairly consistent, not giving me that level of response that I'm really looking for from a control strategy. Okay. So we have to look elsewhere. Now, I think we're at a point where we take a look and see if there are any questions. And I can see on the screen there are no questions. But again, as we're making our way through, please ask the questions. It's always good to hear feedback on what's sparking your interest as we make our discussion. So the final option, and the option we're here really to talk about today, is really about changing the water temperature, which becomes the most viable option when we're trying to balance room temperature. Okay. So from an aspect of heat emitters, and coming back to my baseboard, at 180 degree water temperature, I can get about 600 BTUs per linear foot. Okay. If I drop my water temperature down to 135 degrees, at 135 degrees, I get about 300 BTUs per linear foot. Now, when you start to look at responses, and I compare the water temperature to the room temperature, the relationship between a 65 degree room and a 180 degree baseboard, at 135, it's about half the difference. So if I drop the water temperature by a given amount, I get a fairly consistent response where the heat emitter drops about the same ratio as well. So we start to look at doing changing the water temperature as a methodology of changing or resetting the heat emitter's output. By dropping the water temperature, I get a fairly consistent response out of the heat emitter, reducing the amount of energy. Okay. Now, one of the things that does come into play, and you'll notice when you start to look at convectors, for instance, baseboard, fin tube baseboard is considered a convector. Most manufacturers stop at some point. Here it happens to be 110 degrees. And why you tend to see that drop off at the end here is really this here. Okay. the water temperature passing through that baseboard has to generate the force to force natural convection movement of the air within the room. And the problem is if the temperature here gets down low enough, you may not generate this convective current. So we start to look at doing outdoor reset with baseboard. You tend to see what you have here. Excuse me. You tend to see what you see here, where it doesn't go all the way down to 90 or 85 or 70 degrees Fahrenheit. It normally stops in the neighborhood of probably 105 to 110, as you see here. Okay. But from an aspect of performance, with outdoor reset, if I change the water temperature of the baseboard, I get a good corresponding change in the output of the heat emitter. Same thing when I do air handling units. So if I look at 3.5 gallons here, and I look at the 180 degrees, 140 degrees, 120 degrees, you'll find a little bit of a bigger jump from here to here on the spacing. But if you look at the output of this heat emitter, it's pretty linear through this range from 180 to 120. So I'll see for a corresponding drop in water temperature, I'll see a corresponding drop in the output of the heat emitter. So we start to look at trying to change the amount of temperature coming out of a heat emitter to balance to the outside temperature. If I can change the water temperature, I can change the balance as far as the performance of that heat emitter, whether it's baseboard, whether it's air handling units, or whether it's radiant. Okay, so we start to do outdoor reset. All of a sudden, I start to vary the water temperature. Okay, so if the outdoor temperature changes, where it started off at 0 and up to 35 degrees, I now have half the heat loss that I did under my design conditions. So if I drop my water temperature from 180 degrees down to 135, my heat emitter now puts out half the amount of heat. Half the amount of heat going into the living space balances with the now reduced by a half factor, the amount of heat going outdoors, and my living space stays balanced and comfortable. Also over here, now let's kind of jump back to the heat emitter. The hydronic water temperature inside the heat exchanger is lower. If I have a lower temperature here, my heat transfer from my combustion gases to my hydronic water becomes better. I pick up more sensible heat. And not written in here, but also if this is a condensing boiler, I start to drop the water temperature. Now I give the boiler a better opportunity to condense. So when we start to look at balancing the heat flow in the building, really our best option is to be able to change that water temperature, because by changing that water temperature, I will change the performance of my boiler, change the performance of my heat emitter, stay balanced, stay comfortable. The real key is the reset has to be done based on outdoor temperature. And why we're looking at it through the aspect of outdoor temperature is the outdoor temperature really is the major factor in how much loss the building has. So if we can look at the outdoor temperature, as we see the temperature change, we can anticipate and change the amount of heat input into the building so that we stay balanced. So as the outside temperature goes down on a colder day, we increase the water temperature going into the building, and that increased water temperature balances with the higher heat loss that occurs because the outdoor temperature has gone down. Conversely, if it warms up outside, we sense that outside temperature going up. We lower the water temperature going to the heat emitter. We reduce the amount of heat emitter, and the building still stays comfortable. And through this, we can achieve our objective of a constant room temperature. Okay, so what we'll do is what's called outdoor reset control. And rather than just maintaining the boiler and the system at a constant high temperature and then pulsing the building to maintain room temperature, we now measure the outside temperature. We set up a heating curve, and that heating curve is designed around design conditions. So our design conditions were 0 degrees Fahrenheit, 180 degree water. So the heating curve delivers the design water temperature on the design day, but then as the outside temperature decreases, the boiler water temperature decreases proportionally. And by doing that on a 32-degree Fahrenheit day, we're delivering about 133-degree water temperature. We're staying balanced with the outdoor conditions. The key really is I got to make sure I choose the right heating curve to maintain that temperature. And usually from an aspect of design, it's all about, well, I have to ensure that one end of it is anchored to design conditions. Mine is 0 degrees Fahrenheit, 180-degree water. So I know that becomes one of my tie-in points. Okay, so when we do outdoor reset, one of the things that has to be determined is what's referred to as a heating curve. You may hear it referred to as a heating curve. You may hear it referred to as a reset ratio, or you also might hear it referred to as the slope. So what we're really talking about is the shape of this. This curves actually have a curve to it. Sometimes you'll see them more of as a straight line, but this heating curve sets the combination of the relationship between outdoor temperature and the boiler water temperature. So for instance, if I had a design day of -4 degrees Fahrenheit and my design water temperature was in the neighborhood of about 135 degrees, my heating curve would be about a 1.0. So on the design day, I'd be at about 135-degree water temperature. On a 32-degree day, I'd be somewhere around here, somewhere in the neighborhood of maybe about 110-degree water temperature. But again, that heating curve becomes a combination in the relationship between outdoor temperature and water supply. So for instance, a -4-degree day, they moved up a little bit, it's 140. 23-degree day, 122. A 50-degree day, 95-degree water temperature. And the thing is, if this is the right heating curve, on these days with those water temperatures, the building's going to stay at a constant 70 degrees or 68 degrees Fahrenheit. Okay. And that's really our goal when we start to do outdoor reset control. And what will happen is each building, depending on the design condition, will have a temperature range. So here it's in Celsius, so anywhere from 20 degrees Celsius to 60 or 68 degrees Fahrenheit to 140 Fahrenheit. The water temperature can vary based on outside temperature. If I have an application that has baseboard, so I'm looking for water in the range of about 180 degrees. Okay, so my heating curve is more of a 1.6, -4-degree day, 180-degree water. Now the temperature range now goes from 68 degrees up to 180 degrees. And it's all about making sure that this becomes the right combination to heat that building. Okay. Now, a lot of times from an aspect of setting it up, questions always come up about what the water temperature, what the heating curve needs to be. And typically we look at it and somebody will say, well, you know what? If it's low temperature, it's probably going to be somewhere in here, maybe up to about a 0.8. Medium, maybe up to a 1.4. High temperature, fin tube radiant of fan coils, maybe a 1.4 to maybe a 2.0. Okay. Ideally, somebody has done design on here where you know the outdoor conditions and you know the design water temperature, because if I'm designing off of here, it really becomes an educated guess of where I need to be. But if I can say I'm designing for a 5 degrees Fahrenheit day with 158-degree water, here's my 5-degree temperature, here's 158, it's pretty close to a 1.4. I know that 1.4 curve is the best relationship for my building and my heat emitters throughout that building. Okay. But it really becomes a key point in setting it up. Okay. And then what happens is through this control strategy, then we can set the water temperature and then we start to modulate that water temperature. And again, from an aspect of design, over here, we had the right water temperature for a very short period of time. But when I start to look at modulating the water temperature, it's not just the right water temperature for about 2% of the heating season. This is the right temperature for about 10% of the heating season, so forth and so on. And I can give myself the best match throughout that heating season to put the right amount of energy into the building to maintain comfort in the building. And equally as important, as I drive that water temperature down, the efficiency of the system goes up as well. So I start to run at better efficiencies for larger pieces of time during the course of the heating season. Okay. Now, one of the things that comes into play is from an aspect of design, ideally this would be the heating curve for the building. Because here's my design conditions based on outside temperature and based on water temperature for the heat emitter. Now, a lot of times the heat emitters have a minimum water temperature. So I may have a baseboard that the minimum water temperature is 100 degrees, 110 degrees. Or I may have a air handler that the minimum temperature is 120, maybe 130 degrees. So what has to happen from a standpoint of setting up the heating curve is I may have to make adjustments on the curve to be able to meet the requirements on the design day and also meet the requirements as for the minimum water temperature of those heat emitters. Okay. So a lot of times you end up with a heating curve something like this. Really, the key really is tying it in at the two identified points. What is the minimum water, what is the design water temperature under design conditions? I want that heating curve to hit there. And then what is the minimum water temperature that I want to achieve? Let's achieve that somewhere usually around a 65 to a 68 degree day. And those 2 points do define the heating curve itself. Because ideally, we let, for us, we always like to identify it through a slope, a 1.3, something like that, a 1.6. But with a heat emitter, like heat emitter requirement, it really becomes, let's look at it and identify the two ends of the curves, those 2 points, based on outdoor temperature and water temperature, outdoor temperature and water temperature, and then let's connect the dots between the two. And we'll see this as listed as a slope and a shift adjustment on the control. Okay. Whether it's one other thing when we do this, okay, and a lot of times the discussion comes up about from an aspect of control. Well, if I do outdoor reset, do I really need to zone the building? And the answer always is every building is going to have some level of zoning. But particularly when I have to make an adjustment because of a minimum water temperature, this curve here, the ideal curve, that represents constant circulation, no internal or no external heat demands. So in theory, if this is truly the right curve from the building, without any zoning, I'll maintain a 68 degree day under all outdoor conditions, strictly by changing the water temperature. But because of the minimum water temperature, the minute that this curve rises above the ideal curve, that means I'm putting more temperature into my building than the building is losing. So if I'm putting more temperature in, zoning has to be present in the building to ensure that the building is not overheating. So here, where they both converge, it's constant circulation. The further I move out here, the more I'm going to spend from a standpoint of time where the zone control will be off or closed. Somewhere around here, it might be a 95-5 split, 95 constant, 5% zone closed. I get out somewhere out here, that split now may be a 30-70 or maybe a 40-60 split. But from an aspect of control strategy, just because I'm doing outdoor reset, in most systems, particularly systems where there is a minimum water temperature from a heat emitter, that zoning is, I still want to see zoning in that building. Yeah. And again, from the aspect of the question being asked, this is one that I get on a regular basis when I'd worked as for a manufacturer's rep firm. Do I need zoning? And the reality, when you start to look at this building, there's a lot of things that play into that zoning. Throughout the building, there's going to be internal and external gains on that building. Outdoor reset in and of itself without feedback isn't going to accommodate those. So there's going to have to be zoning to take care of those. It may be because of the lifestyle of the individual. So different rooms may want to be different temperatures. It may be also be based on the occupants of the building. It may be because certain members of the building like different temperatures, because of their age, for instance, there may be a requirement of a different temperatures. The styles of the heat emitters may dictate zoning, variations in the construction. And then the catch-all is when we start to look at, set up the heating curve. If I have zoning throughout the building, if the heating curve happens to be set higher, it still helps to maintain comfort in the building. So from a design standpoint and a control standpoint, it really is all about mixing it all together. So when I do zoning, it ensures that we're able to tailor the internal comfort for anything that varies within that building itself. So it really brings it all around. And with outdoor reset, in most cases, the zoning really is acting as a high limit. So I'll put the right water temperature to achieve a potential temperature, and then the zoning allows the system to cut back on the amount of heat that's going into that building if the heating curve and the heat emitters is providing a little more heat than actually is needed in that building. So from a piping and control standpoint, I may have a boiler with some methodology of doing outdoor reset control, as seen by the outdoor temperature here, and this sensor strapped on the pipe here, providing the best water temperature needed here. But then because of all variations, let's add an extra level of zoning, so that if there is any variation, say, between these 6 zones, the zoning will allow us to tailor that part of the building for the exact needs of that section of the building. So, with outdoor reset, if a lot of times a question comes up about zoning, my answer always is I'd like to see both in the building because of all those factors we talked about a couple of slides ago. Okay. Now, when we set it up, I've kind of thrown some terms out there in the setup, but in order to really tailor the heating curve, there are a few adjustments that can be made. And I'm going to actually work with our descriptions of our terminology: slope, shift, and room temperature. And all 3 of these are built in together to be able to tailor the comfort in the building. The first one I kept on throwing out, I've thrown out a number of times, is the term slope. You'll hear it referred to as the curve or the reset ratio. So with the slope, what we're really doing is it's a curve, it's a shape, and it's in a number anywhere from 0 to here we showed up to 2.6. And this sets the ratio, the change between changes in outside temperature and changes in water temperature. And what will happen is, as the outside temperature changes, the water temperature changes, and what that will do is it will potentially maintain a constant room temperature in that process. Okay. Now, I'm going to actually jump down to the bottom to room set point temperature. This happens to be this curve over here. So what I'm doing is when I make a room temperature change, I'm grabbing this fan of curves, this series of curves, and dragging that point up or down, which effectively will change the room temperature set point. So if I drag it up here, if I drag that whole fan up, the ratio change stays the same, but it's going to add up because it's tied in here. That ratio change is now corresponding to a 25 degrees Celsius room temperature or 77 degree Fahrenheit temperature, not 68. But the end result is if I change the room temperature here, that proportionality stays the same, and the room temperature should stay constant from from a mild day to a cold day. Okay. Now the final thing is what's called a shift, or a shift. I'm vertically shifting the curve up this axis here. Now what's important about that is when I make that shift, the shift is proportionally heavier on the change that occurs in the mild days than it does on the colder days. Okay, but it allows me some way to anchor the curve at another point. And a lot of times the shift happens if somebody complains about the room temperature dropping or not being comfortable just under the mild days. Okay, So from adjustment standpoint, you have a slope, you have a shift, and you have a room temperature set point. And through these three separate adjustments, it allows you really to tailor the shape and the location of the curve to meet the requirements of the home under a wide variety of conditions. Now, one thing about this, the slope and the curve, I keep on talking about, these numbers here, and we talk about A, B, and C under certain conditions. So for instance, I'm always saying if I need 180-degree water, I'm at about 1.6. Thing to remember with these curves, it comes up every once in a while, is the curve is also location specific. So for instance, 1.6 curve does give you 180-degree water temperature when you're somewhere around 0 to -4-degree day. But if my design day is only 23 degrees and I need 180-degree water, that 1.6 curve isn't going to get me anywhere near it. That heating curve for a 23-degree outdoor temperature, that's more of a 2.0 curve. If I'm up around 43 degrees, think somewhere in maybe San Francisco, California, maybe somewhere a little bit south of there, and I need 180-degree water, that's about a 2.6 curve. So when we start to look at this, the thing to remember is the setup of it. I said it earlier, the heating curve is really based on outdoor temperature and water temperature. But for the same water temperature, depending on your location, which will also determine your design outdoor temperature, 180-degree water temperature could be anywhere from a 1.6 curve up to a 2.3 or potentially even higher. So it is something to remember when you start to look at setting these curves and where are you located. I say in the world, but we'll go North America because that's our main grouping of our presentations. Okay. Now, a couple other things to be concerned with. You start to look at heating curves and you start to look at how things are performing. And a lot of projects for multiple water temperatures will offer mixing valves. Here happens to show a non-condensing boiler with a 4-way. It could also be a condensing boiler with a 3-way as well. And why this is important is if I have the boiler set up on its own heating curve to provide a certain water temperature prior to the mixing valve, the thing with the methodology of the boiler control is not only does it look at the water temperature for its programmed heating curve, it also looks at the requirements of any mixing device or any other device that's associated with it. So let's say we have this mixing valve B here, and that mixing valve B is running on this curve here, this 1.2 curve. In the logic of the boiler, it knows that the motorized mixing valve needs a temperature that's 14 degrees hotter so that valve stays in a good operating range. It's not on one extreme or the other. So because of that, when a boiler looks at its heating curve, you may have a heating curve program, but always in the program, working in the back, is this dotted line curve here. That's my differential curve as dictated by the curve that's set up with the boiler. Why that's important is when I look at the boiler control, not only does it look at the actual heating curves of the mixing valves and the high temperature circuit, but it also compares it to, I'll call it the differential temperature curve of each mixing valve. So what you may end up with from a boiler standpoint, and I'm going to look at the high temperature. Let's say I have two mixing valves. This happens to be one mixing valve with this heating curve. This green line is the second mixing valve heating curve. But what happens is when I look at the boiler maintains its differential temperature, this 14 degrees temperature, always above and beyond the mixing valves. So you notice I have two nice smooth curves set, but when I look at my boiler control, the boiler control curve is not smooth because the boiler control is trying to maintain the right differential above each one of these mixing valves. These could be mixing valves. It could also be a set point in there. There could also be another heating curve for high temperature as well. When we start to look at the temperatures that the boiler is operating for its outlet temperature, the thing to remember is from the aspect of outdoor reset control, particularly with the higher level controls, is there's a lot of things going on in the background that's driving that boiler water temperature. The end result is if you're looking at the water temperature, the boiler may not be operating off of the outdoor temperature you're expecting it to see because of the other requirements of the boiler to make sure that it's meeting all the demands of the loads on it. Okay. So kind of get into the summary stuff here. We talked a lot about the what, the hows. Yeah, how do we do it? The real question is, why do we do it? Well, the first thing is, why do we want to do outdoor reset? It's really, first one's really about comfort. Okay. If I want a building to be comfortable, the building is much more comfortable if there's a constant input of energy into the building at a fixed, providing for a fixed temperature, rather than pulsing the building periodically and with the maximum amount of heat that the heat emitter can put out. So it's all about maintaining comfort. You know, it gives me nice slow temperature changes. I'm not pulsing it with the full output of the heat emitters. It's a constant heat into the building. Think of it as keep up versus catch up. You know, so from the aspect of performance and you're looking at it from comfort, that becomes one of the driving factors behind doing outdoor reset. The other one is it's all about efficiency. If I run outdoor reset, I can run more efficient. I'm matching the load to the building. Okay. You know, from the aspect of building performance, I'm not putting the energy into the building that the building is going to overheat. In the past, when I'd worked for a rep firm and I worked a little bit closer to the jobs, it was always interesting to hear from building owners, somebody that owned apartment buildings that had a central heating plant that the tenants didn't pay for the heat. And prior to doing a boiler with outdoor reset, you'd look at the apartment building and there'd be all kinds of windows in the building that the windows would be opened up a crack because the heat emitter was putting more energy into the building than the building was losing. So they had enough extra energy that they could lose more energy and still be comfortable in the building. Okay. When you do outdoor reset, you're putting the right amount of energy in that building, the windows go closed. You have really better comfort, but also better economy because of the fact that you've now started to control the heat loss of the building. You know, I drive my efficiency, I burn less fuel. Also, my standby losses also drop as well because of the fact that my water temperatures aren't as high. I don't turn a pump off and all of a sudden everything's sitting there with 180-degree water, losing this heat that's been paid for. Okay. I'm running constantly at a lower water temperature. The standby losses are less. And because I'm running constantly, there's less starting and stopping, there's less wear and tear on the equipment. Okay. Now, particularly if I'm doing a condensing boiler, outdoor reset's really where the saving is built. So this happens to be a curve showing the efficiency of a condensing boiler versus inlet water temperature. Standard curve out of the ASHRAE manual. So if I run at a design outdoor water temperature of 180 degrees with a 20-degree drop, and I'm doing a condensing boiler, from the generic numbers, that works out to a little bit more than 86% efficient. But if I can drop that water temperature through outdoor reset control, let's say I drop it down to 120, all of a sudden that 86.5% efficiency goes up to 90%. The lower the water temperature, the higher the efficiency can be. You know, if I get it down to 100 degrees, I'm in the neighborhood of about 94% efficient. So when you start to look at doing outdoor reset, there's definitely a comfort argument to be made for it. But if I'm doing a condensing boiler, there also is a very big efficiency argument to be made as well. And when I do baseboard, I can do baseboard at 180 going out and 160 going back, as well as 120 or 110 degree water going out, 100 degree water. So these numbers here, this 94 number, that is an achievable number with air handlers and also with baseboard. Okay? And the thing is, when I start to do a existing building, you know, a lot of times the argument says, you know what, if I do an existing building, I'm going to do a condensing boiler, but I'm not going to get much efficiency out of it because of the required water temperatures. If you do outdoor reset, that relationship can change. So here we're looking at the ASHRAE data for Boston, Massachusetts. Okay. And here's my supply at 180. Here's my return at 120. We do about condensing boilers. We always talk about return water temperature. This yellow line across here, that's 130 degrees. Let's call that the dew point for my condensing boiler. What that really means to me is if my return water temperature is above 130, the boiler is not condensing. If it's below 130, it is condensing. So if I do outdoor reset on the design day, I might only be delivering 86.5, maybe 87% efficiency. But when the outside temperature gets in the neighborhood of about 22 degrees Fahrenheit, 20 degrees Fahrenheit, all of a sudden the return water temperature crosses that dew point, and now I'm starting to condense. And you look at this, and from an aspect of condensing, the boiler may not condense on the design day, but from an aspect of performance, that boiler's condensing for greater than 90% of the heating season. In fact, let's tie in a couple of points here, back to the previous slide about the generic efficiencies. This point right here, which represents about 120 degree return water temperature. With 120 degree return water temperature, that represents about 90% efficiency. So that boiler that's not efficient on design day will be 90% efficient for about 88% of the heating season. If I can bring the temperature down even lower on that heating curve, let's say I can go out at about 110 and come back somewhere near 100. Coming back at 100, that represents about 94% efficient. That boiler can be at least 94% efficient for about 51% of the heating season. So when I start to do outdoor reset control, particularly with condensing boilers, even with baseboard, I still can see really good efficiency numbers, even though under design conditions, the boiler may not condense. And this is really the power of doing outdoor reset with a condensing boiler. So, covered a lot of ground during the course of this presentation. We explained how heat flow process from the burner to outdoor and how outdoor reset can control it. And it's really about 3 transfers. Yeah. Across the heat exchanger in the boiler, across the heat emitter in the building space, across the wall of the building, and how we can balance them with outdoor reset. We talked about the benefits of it. We talked how outdoor reset works, and we talked about selecting a heating curve. So, let's take a look and see if we have any other questions or have any questions. So Miranda, it appears we do not have any questions.
I don't think we do, Jody.
So first off, before I hand it over to Miranda, I'd like to thank you all for attending, and please keep track of what we're doing and come join us again. And with that, I'm going to hand it to you, Miranda.
Thank you, Jody. Just a few reminders before we close out. A recorded version will be available in the next 2 weeks or so on the Video Library and YouTube channel. Make sure you fill out that survey that you will receive by the end of the day today, especially if you would like that PDH credit, as it is mandatory. And then if you have any additional questions or anything pops up, feel free to email the email on the screen right now. We will be putting together a Q&A spreadsheet of all of the questions asked in last week's session, and if we get any questions in from this one. So keep an eye out for that email as well. And then Thursday, we have our last November online seminar on the BMS Gateway. If you would like to register, feel free to go to the website and register up until the time of that seminar. And within the next week or so, we will be posting a December schedule, so keep an eye out for that announcement. And that does conclude today's webinar. So thank you for attending and have a great day.